everyone, welcome to today's Explainer. We are literally pulling back the curtain on reality itself today. We're going to reveal this hidden mathematical language that unites wildly different physical systems. So, if you enjoy finding the hidden structures behind complex ideas, well, you are absolutely in the right place. All right, let me pose a bit of a mystery to you. What exactly do a mass bouncing on a spring, a massive forest fire spreading across a landscape, and the very fabric of space-time itself, what do they all have in common? I mean, on the surface, absolutely nothing, right? But underneath, it turns out they share the exact same underlying structure. Okay, let's dive into this. The answer to our mystery is actually graph theory. It acts as this ultimate mathematical blueprint that perfectly bridges everyday physical systems and pure network topology. It basically takes our incredibly messy universe and reduces it into this beautifully simple game of dots and lines. Now, to really grasp how powerful this is, we kind of need to shift our perspective. See, at every scale of the universe, physicists traditionally ask one big question: which objects interact with which other objects? But graph theory, it takes a totally different approach. It completely strips away the physical form. It doesn't care what the object looks like at all. Instead, it focuses strictly on connectivity, literally just what is connected to what and exactly how strongly. Now, what's really interesting about this is how it acts as our universal Rosetta Stone. Basically, a simple dot, or a vertex, can represent a particle, an atom, or even a space-time event. A line connecting them, an edge, is a force bond or a causal path. Add a weight to that edge, and you've got your coupling strength. Add an arrow, boom, you dictate the flow of time. It's just an incredibly elegant way to encode reality. Section 1. The graph Laplacian engine. Okay, so don't let the math here intimidate you. The Laplacian matrix is really just the beating heart of how things move. Think of it kind of like peer pressure. Action is determined entirely by how different you are from your direct neighbors. It's just simple subtraction. The degree, meaning how many connections touch a point, minus the adjacency, which tells us exactly who those neighbors are. Watch how this works in practice with a classic physics problem: masses connected by springs. This single Laplacian matrix we're looking at, which is derived entirely from the basic graph connectivity we just talked about, it perfectly encodes all three masses and every single one of their spring connections. And here's the crazy part. Without measuring a single physical distance, this equation of motion predicts the system's natural patterns of vibration purely by analyzing the graph. So the crucial point here is that this isn't just some abstract mathematical exercise. The graph Laplacian is literally a universal accounting system. It's the ultimate engine of flow. It dictates everything from electrical circuits balancing their current, right down to how heat diffuses across a highly complex material network. It all uses the exact same engine. Section 2. Translating the physical world. Let's start small here with the Ising model, which basically shows how local microscopic connections create global magnetism. The graph structure dictates which atomic spins can actually align. But check out the triangle setup. This represents a massive mathematical paradox known as geometric frustration. If the rules say that neighboring nodes must have opposite spins, like we see in antimagnetism, this triangular topology makes it literally impossible for that third node to satisfy both of its neighbors at the same time. It's basically the mathematical equivalent of being stuck between two friends who absolutely refuse to speak to each other. The network structure itself literally creates physical tension. So from that microscopic lattice of frustrated magnets, we can actually seamlessly scale up our graph theory tools. We can use them to understand massive, large-scale events, things like natural disasters, fluid flows, and sudden phase transitions. And this brilliantly illustrates percolation theory. Imagine a grid where microscopic links just randomly open up. At a low probability, you just get isolated, disconnected clusters. But right at a specific critical mathematical threshold, boom, a giant connected cluster suddenly spans the entire system. This is the exact mathematical moment a material suddenly starts conducting electricity, or the terrifying moment enough tiny links align for a forest fire to just rapidly spread across an entire landscape. Now, I want you to consider this quote for a second. Rather than classical particles moving sequentially, quantum amplitudes wave through the graph. Wow, that is profoundly beautiful. We are now pivoting entirely out of classical physics and stepping right into the strange, highly probabilistic world of quantum mechanics. Because in the quantum realm, things get incredibly chaotic, right? But graph theory, it brings order. Take Feynman diagrams, for instance. These aren't just pretty pictures. They are literal network graphs where vertices are interaction events. They organize the infinite chaotic possibilities of particle scattering. And then we have quantum walks. Instead of a particle just randomly bouncing from node to node, quantum amplitudes actually wave through the entire graph. And the pure network topology alone dictates exactly where those waves interfere constructively to exist or destructively to completely cancel out. So we've gone from springing masses to magnets, all the way to quantum interactions. Now, let's scale up to the ultimate network. We are going to apply graph theory to the largest and absolutely most profound physical system imaginable. Let's move to and see how this builds right into the absolute cutting edge of modern physics, quantum gravity. In general relativity, we are taught that spacetime is this smooth geometric fabric, but here, spacetime is modeled discretely as a causal set. It's a graph. Vertices are events, and directed edges represent the ultimate relativistic rule, exactly which events can physically affect others. Spacetime itself becomes nothing but a vast, interconnected web of cause and effect. Section 3. Topology over geometry. Now, we must firmly remember this. The map is not the territory. A super common mistake is thinking a graph drawing represents actual physical geometry. Let me be clear, it absolutely does not. Whether nodes are drawn in a perfectly straight line or bent into some extreme curve, mathematically, they are exactly the same. Unless we explicitly code physical distances in as edge weights, exact physical distances and visual angles are entirely 100% irrelevant to the graph. It all boils down to this really fundamental contrast. Physical geometry, it cares about continuous fields, actual measuring cape distances and real physical angles. But mathematical topology, it cares only about strict connectivity, abstracted vertices, and edges. And what we've really learned today is that when it comes to finding the underlying universal blueprint of reality, strict topology rules over geometry every single time. Which brings us to a seriously mind-expanding question. We've seen how graph theory models everything from bouncing springs to quantum waves. So if graph theory can perfectly model space-time itself at the very smallest scales, is the universe truly a smooth, continuous space like we perceive it? Or is reality at its very core just the ultimate network of discrete dots and lines? It's a fascinating thought to chew on, isn't it? Keep exploring, stay curious, and thanks so much for joining me for this explainer.